After you've mastered how to write electron dot formulas on a piece of paper, which is a flat sheet and we're kind of limited to the two-dimensional world, you have to really start thinking about how molecules really look in a three-dimensional world, because that's the world that molecules actually live in. The simplest model for modeling this type of behavior, and it actually works rather well, is called the valence shell electron pair repulsion theory. And the name's probably scarier than it actually is as far as it works. We often just call it the VSEPR theory, and then we kind of just say it all together, VSEPR theory. So you'll hear me say VSEPR theory from now on when I mean the previous. So the way it works, and the name kind of gives it away, is you take your electron dot formula and you simply count electron regions around the central atom, and you realize that each of those regions is a negatively charged region. And so it's going to repulse all the other negatively charged regions, and they're going to try to get away from each other. They can't completely get away, though, because the nucleus of the central atom is holding them in. So what they do is they try to get away from each other, but they're still held by the central atom. This leads to distinct molecular shapes. And the easiest one is two regions. If you only have one atom on one side and one on the other, and they try to get away from each other, you get a fairly linear type molecule. And so that's the first one. Two regions gives you linear shape. The bond angle is 180. Stepping up to the next one, three regions. You count the regions around the central, there's three. If three regions try to get away from each other, you basically get a nice kind of pie shape. It's like taking a pie and cutting it into perfect thirds. So you get a 120-degree angle all the way around for those three regions. Both of those regions are still planar. They still look just fine on a sheet of paper. It's when you get to four regions that you have to go to the third dimension. You have to go three-dimensional. And what this gets you is a shape that we call a tetrahedron or tetrahedral geometry. It's four regions around a central, all perfectly symmetric. And if you take a look and spin the molecule around and look at it, every region is equivalent. And the bond angles are now down to 109.5 degrees. That's a tetrahedral geometry. So as you can see, the bond angles are getting smaller because we're bringing in more regions. We started at 180 for linear, 120 for trigonal planar. Now we're down to 109.5 for tetrahedral. So that really sums up most of what we will use, especially in organic chemistry. Now, in addition to those, you can have expanded octets, which gets you 5 and 6 regions. So to handle those, you got to go one step further. The 5 regions is a little bit complicated, but it's really just a combination of 2 and 3. You're going to have 2 atoms linear, and then the other 3 are going to be trigonal planar perpendicular to that. When you look at the shape, you see what we call a trigonal bipyramid. We call it a bipyramid because you can look at the pyramid going up to the top atom and down to the bottom atom. Those are 2 little pyramids pointing in opposite directions. That's trigonal bipyramid. The last one is 6 regions, and when you get up to 6 regions, you get something that should look somewhat familiar if you've ever studied XYZ coordinate planes and coordinate points. Everything's 90 degrees apart or 180. It's like the X, Y, and the Z axis of three-dimensional space. You put 1 atom in each space, you get 6 total. Bond angles are either 90 or they're 180. You might go, why is it octahedral when there's 6? Well, if you close up, if you take every point and make a line, you get a closed three-dimensional object with a total of 8 sides. 8-sided enclosed figure is an octahedron, and so we call it an octahedral geometry. So those are the other 2 that are part of VSEPR theory. When you put all 5 of those together, you've got all 5 of what we call our electronic geometries around a central atom. And that is at the heart of VSEPR theory.